Look up on a clear night, away from the glow of city lights, and you'll see them. Not all of them, not with your naked eye alone, but you'll know they're there. Venus, brilliant and steady in the evening or morning sky. Mars with its subtle reddish tint. Jupiter, bright and unwavering. Saturn, fainter but still visible if you know where to look. Mercury, elusive, hugging the horizon near sunset or sunrise. And the others, Uranus and Neptune, invisible without a telescope but present nonetheless, distant sentinels at the edge of our cosmic neighbourhood. 8 worlds, 4 small and rocky, huddled close to the warmth of the sun. 4 giants, massive and strange, orbiting in the cold outer reaches. This arrangement feels natural to us. It's the only planetary system we knew for most of human history, so of course it seemed like the template. The standard way that stars gather families of worlds around themselves. When we finally began discovering planets around other stars in the 1990s, many scientists expected to find solar systems that looked more or less like ours. Small rocky planets near the star, gas giants farther out, everyone in relatively circular orbits, spaced at comfortable distances from one another. We were wrong. Magnificently, wonderfully wrong. The universe, it turns out, builds planetary systems in ways we never imagined. We found giant planets orbiting closer to their stars than Mercury orbits our sun. Scorched worlds where a year lasts just a few Earth days. We've discovered systems where all the planets are similar in size, lined up like peas in a pod, nothing like the dramatic size difference between Earth and Jupiter. We've found worlds larger than Earth, but smaller than Neptune, a size category completely absent from our own system. In all this cosmic diversity, among the thousands of planetary systems we've now catalogued, one particular configuration stands out for its rarity. Ours, the solar system, our home, appears to be unusual. Not impossible, not unique, but uncommon in ways that have only become clear as our census of other worlds has grown. Recent studies suggest that planetary systems with our particular architecture, what scientists call an ordered system, where planetary masses generally increase with distance from the star, represent perhaps only 1 to 5% of the multi-planet systems we've discovered so far. We are, it seems, living in a cosmic arrangement that doesn't follow the most common patterns. This raises a question that feels both scientific and deeply personal. Why? Why did our solar system form the way it did? What sequence of events, what chain of circumstances led to this particular configuration of worlds? And perhaps most intriguingly, was any of this necessary? Could things have unfolded differently, producing a completely different arrangement of planets? Or was something about the early solar system destined to create what we see today? Tonight, we're going to explore these questions. We'll travel back 4.5 billion years to witness the birth of our planetary system, watch as worlds take shape from swirling dust and gas, and discover why the orderly arrangement we take for granted is actually the product of chaos, violence, and what might have been extraordinary timing. We'll see how Jupiter nearly destroyed the inner solar system, how Saturn may have saved it, and how the Earth you're resting on right now is the result of processes that, had they played out even slightly differently, might have left our corner of space looking completely alien. So settle in. Let your breathing slow. Allow your mind to drift back through time, back to when the sun was young and surrounded by a vast disk of material that would, over millions of years, coalesce into the family of worlds we call home. The story begins not with planets at all, but with dust. The dusty cradle. 4.6 billion years ago, in what would one day become a quiet suburb of the Milky Way galaxy, a massive cloud of gas and dust began to collapse under its own gravity. This wasn't unusual. Stars are born this way all the time throughout the galaxy. from clouds of hydrogen and helium enriched with heavier elements forged in previous generations of stars. This particular cloud, measuring perhaps 30 to 50 times the distance from where Earth would eventually orbit the Sun, contained everything needed to build a star and its retinue of planets. The collapse began slowly at first, triggered perhaps by the shockwave from a nearby supernova or by the gradual accumulation of material pushing the cloud past some critical density threshold. As gravity pulled inward, the cloud began to spin faster. This wasn't a new rotation, but an amplification of whatever gentle motion the cloud already possessed. The laws of physics demand that angular momentum be conserved, so as the cloud's radius decreased, its rotation rate increased, just as a figure skater spins faster when pulling their arms inward. This spin had profound consequences. While gravity pulled material inward from all directions, centrifugal force from the rotation resisted collapse in the direction perpendicular to the spin axis. In the direction parallel to the spin axis, along the poles, material could fall freely. The result was inevitable. The cloud flattened. What had been a roughly spherical mass became a disk, with most of the material concentrating in a plane perpendicular to the axis of rotation. At the center, where most of the mass accumulated, temperatures and pressures rose until nuclear fusion ignited. The Sun was born. But surrounding this newborn star was something equally remarkable: the protoplanetary disk, sometimes called the solar nebula. This was the dusty cradle from which planets would emerge. Picture it, if you can. A disk of gas and dust extending outward from the infant Sun for hundreds of astronomical units, one astronomical unit being the distance from the Sun to where Earth would eventually form, about 93 million miles. The disk wasn't uniform or placid. It roiled with turbulence threaded with magnetic fields, heated by the Sun at its center and cooled by the darkness of space at its edges. Near the Sun, temperatures exceeded 1,500 Kelvin, hot enough to vaporize most substances. Farther out, in the region where Jupiter would form, temperatures dropped below 200 Kelvin. Beyond about 3 to 4 astronomical units from the Sun lay the frost line, also called the snow line, where temperatures fell low enough for water ice to condense. This temperature gradient would prove crucial to everything that followed. Inside the frost line, only materials with high condensation temperatures could exist as solids. Metals like iron and nickel, rocky minerals like silicates. Beyond the frost line, not only could these materials condense, but so could vast quantities of ices, water ice, methane ice, ammonia ice. This effectively tripled the amount of solid material available to build planets in the outer solar system compared to the inner region. It's no accident that the giant planets formed where they did. The composition of this disk tells us something remarkable. 99% of it was gas, primarily hydrogen and helium, with only 1% consisting of solid dust particles. Yet that 1%, that seemingly insignificant fraction of heavier elements, was enough. The dust grains were tiny, typically around 1 micrometer in size, smaller than a grain of pollen. They were composed of silicates, metals, carbon compounds, and in the outer disk beyond the frost line, ices. These microscopic specks drifted through the gas, colliding occasionally, sometimes sticking together, sometimes bouncing apart. We can observe disks like this around young stars today. The Atacama Large Millimeter Array, a collection of radio telescopes in the Chilean desert, has captured stunning images of protoplanetary disks around stars in nearby star-forming regions. The images reveal intricate structures, concentric rings, spiral arms, gaps, and asymmetries. Some of these features are thought to be the signatures of planets forming in real time, carving channels through the disk as they grow, pulling material toward themselves while simultaneously clearing their orbital paths. The disk around the young sun probably looked similar to these systems, though we can never know its exact structure. Studies of meteorites, the most primitive rocks in our solar system, tell us that the disk was isotopically heterogeneous, meaning that material from different parts of the disk had subtly different chemical fingerprints. This suggests that the disk didn't mix thoroughly or instantaneously. Instead, material accreted onto the disk over time from the collapsing molecular cloud, with different regions retaining some memory of where they originated. The disk was also turbulent, likely driven by the magnetorotational instability, a process where magnetic fields threading through the gas amplify any small perturbations, generating eddies and turbulence. This turbulence had competing effects. It helped transport angular momentum outward, allowing material to fall inward toward the sun, but it also stirred up dust particles, preventing them from settling into a thin layer where they could more easily collide and grow. Within the first few 100,000 years, material from the disk accreted rapidly onto the young sun. The accretion process wasn't smooth or steady. Studies of young stellar systems suggest that protostars go through episodic accretion events, periods of intense infial interspersed with quieter phases. During these outbursts, the disk would have glowed brightly in infrared light, heated by the energy released as material spiraled inward. But even as material fell onto the sun, even as the disk slowly drained itself, something else was happening in the swirling gas and dust. Solid particles were beginning to find each other, to stick together, to grow. The process was slow at first, incremental, building from microscopic dust grains to pebbles to boulders. But once it began, it set in motion a chain of events that would, over the next few million years, transform this disk of gas and dust into a system of worlds. The disk's lifetime was finite. Observations of young stars suggest that protoplanetary disks typically last between 3 and 10 million years before dissipating, their gas driven away by stellar winds, photoevaporation, and accretion onto the star. This ticking clock would prove crucial. Planets had only this window of time to form, while substantial amounts of gas remained available. Once the gas dispersed, the rules would change dramatically. Within the disk itself, different regions behaved differently. Close to the sun, ultraviolet radiation from the young star heated the gas and drove powerful winds that carried material away from the inner edge of the disk. Farther out, the disk was cooler and denser, creating ideal conditions for planet formation. The boundary between these regions constantly shifted as the disk evolved, creating a dynamic environment where the rules for planet formation changed with both time and distance. The disk wasn't smooth or uniform. Like Saturn's rings on a much larger scale, the solar nebula likely contained gaps, spirals, and concentrations of material. These structures formed through a variety of mechanisms. Gravitational instabilities in the disk could create spiral arms, regions of enhanced density that swept through the disk like waves. Magnetic fields threading through the ionized gas created zones of turbulence and zones of relative calm. And as the first large planetesimals formed, their gravity began to create gaps and resonances, clearing material from some regions while concentrating it in others. The temperature gradient across the disk created distinct chemical zones. Close to the sun, only the most refractory materials, substances with the highest melting and boiling points, could condense into solid form. These included metals like iron, nickel and aluminum, and rocky minerals like olivine and pyroxene. Volatile materials, those that evaporate at lower temperatures like water, methane and ammonia, remained gaseous. But beyond the frost line, everything changed. The temperature dropped below about 170 Kelvin, cold enough for water ice to condense. This single fact had enormous consequences. Water was abundant in the solar nebula, making up a significant fraction of the heavier elements. Beyond the frost line, the availability of water ice effectively tripled the amount of solid material available for planet building. Add in other ices like methane and ammonia, and the enhancement was even greater. This is why the giant planets formed where they did. Beyond the frost line, planetary cores could grow larger and faster because there was simply more material to work with. A core forming at Jupiter's distance had access to 3 times as much solid material as one forming at Earth's distance. This head start would prove decisive. The disk's evolution was also influenced by the young sun's activity. Protostars are variable, going through periods of intense activity interspersed with quieter phases. During active periods, stellar winds intensified, photoevaporation increased, and accretion rates surged. These variations created episodic changes in the disk, alternately feeding it with new material from the collapsing molecular cloud and stripping away its outer layers. The disk was not a static environment, but a dynamic, evolving structure, and the planets formed in this constantly changing medium. And so the stage was set. The sun burned at the center, young and bright and active. The disk spun around it, hot in the inner regions, cold in the outer reaches, rich with gas near the star, enhanced with solid material beyond the frost line. Turbulence churned through the gas. Magnetic fields created structure and instability. Temperature gradients separated volatiles from refractories. And everywhere, dust particles drifted, collided, stuck together, began the slow process of transformation from microscopic grains to massive worlds. In this environment, from these ingredients, the solar system would emerge. But the path from dust to planets was neither straightforward nor gentle. It required growth, collision, migration, and transformation. It required violence and chaos before order could emerge. When dust becomes worlds. The journey from microscopic dust grain to planets spans a vast range of sizes, some 30 orders of magnitude, from particles smaller than bacteria to objects thousands of kilometers across. At each step along this journey, different physical processes dominate, and each step presents its own challenges and mysteries. The first stage, the growth from micrometer-sized dust grains to millimeter and centimeter-sized pebbles, occurs through a process called coagulation. When dust grains collide in the disk, they can stick together through a combination of electrostatic forces, van der Waals forces, and in the case of icy particles, cold welding. These forces are remarkably effective at small scales. Laboratory experiments have shown that fluffy dust aggregates can stick together quite readily when they collide at low relative velocities, building up larger and larger particles. But there's a problem. As particles grow larger, they become more vulnerable to destructive collisions. Instead of sticking together, they can shatter on impact, fragmenting back into smaller pieces. This creates a bottleneck. Particles can grow readily up to about a centimeter in size, but getting past this barrier requires that collision velocities remain low. In a turbulent disk, maintaining gentle collision speeds becomes increasingly difficult as particles grow. There's another challenge as well, one that threatened to end planet formation before it could truly begin. As particles grow, they begin to interact with the gas in the disk in a way that causes them to lose orbital angular momentum. The gas orbits the Sun slightly more slowly than solid particles at the same distance, because it's partially supported by pressure gradients. When a solid particle moves through this gas, it experiences a headwind, a drag force that causes it to lose energy and spiral inward toward the Sun. For meter-sized objects, this inward drift is fastest. occurring on timescales of just 100 to 1,000 years. This is the radial drift barrier, and for decades it puzzled scientists studying planet formation. If meter-sized objects drift into the Sun so quickly, how do planets ever manage to form? Several solutions have been proposed. One possibility is that particles don't grow smoothly from centimeters to meters to kilometers. Instead, they might jump directly from small pebbles to much larger bodies through gravitational instabilities. If the dust settles into a thin enough layer in the disk, the layer itself can become gravitationally unstable, fragmenting directly into kilometer-sized objects called planetesimals. Computer simulations suggest this can happen if the dust-to-gas ratio in the disk's midplane becomes high enough, creating a layer massive enough to collapse under its own gravity. Another solution involves the concentration of particles in local pressure maxima in the disk. Imagine eddies in the gas, swirling vortices where particles can become trapped and concentrated. As particles accumulate in these regions, their local density increases, potentially triggering gravitational collapse into planetesimals, even if the disk as a whole isn't unstable. Evidence for such particle traps has been seen in observations of protoplanetary disks, where bright asymmetric structures suggest regions of enhanced dust concentration. Once planetesimals form, however they manage to do so, the next phase of growth becomes somewhat easier to understand. Planetesimals interact primarily through gravity. When two planetesimals pass near each other, they gravitationally tug on each other's orbits. Occasionally they collide, and in most cases collisions result in mergers, building larger and larger bodies. This stage is called oligarchic growth, because the largest bodies in a given region tend to dominate the accretion of nearby material. The reason for this dominance is subtle but powerful. A larger planetesimal has a stronger gravitational pull, which means it can reach out farther to attract other bodies. It also has a large collision cross-section, the effective area within which a collision will occur. Most importantly, as a planetesimal grows more massive, it begins to gravitationally scatter nearby smaller bodies, stirring up their orbits and creating more opportunities for collisions. This leads to a runaway effect. The larger a body becomes, the faster it grows, and the gap between the largest and smallest bodies in a region widens over time. This runaway growth phase produces what scientists call planetary embryos, moon-sized to Mars-sized objects that dominate their local feeding zones. In the inner solar system, these embryos likely reach masses of a few percent of an Earth mass within the first few million years. Beyond the frost line, where more solid material was available, embryos could grow even larger, potentially reaching masses comparable to Earth within a similar time frame. But there's a competing theory for how planets, particularly the giant planets, grew so large so quickly. This is the pebble accretion model, which has gained considerable attention in recent years. In this scenario, planets grow primarily by accreting small pebbles drifting inward through the disk due to gas drag. Once a planetary embryo reaches a certain size, perhaps a fraction of an Earth mass, it becomes efficient at capturing these drifting pebbles. As pebbles approach the embryo, the gas flow around it causes them to lose energy and spiral inward onto the growing planet. This process can be remarkably fast, potentially allowing planetary cores to reach tens of Earth masses within a few 100,000 years. Which of these processes dominated in the early solar system? Recent evidence suggests a nuanced answer. Isotopic studies of Earth and Mars, analysing the abundances of different elements and their isotopes in rocks from both planets, reveal that these worlds formed primarily from material in the inner solar system. The contribution from the outer solar system, beyond Jupiter's orbit, appears to be limited to just a few percent by mass. This finding argues against pure pebble accretion from the outer disk and favours a formation mechanism dominated by the collisions of inner system embryos. However, this doesn't mean pebble accretion played no role. It's quite possible that pebble accretion was crucial for rapidly growing the cores of the giant planets beyond the frost line, where drifting ice-covered pebbles provided abundant material. Once Jupiter's core reached about 10 to 20 Earth masses, it would have been massive enough to begin capturing gas from the disk, eventually growing into the gas giant we know today. For the terrestrial planets, though, collisional growth among local embryos appears to have been the dominant mechanism. The process of building planets from planetesimals and embryos wasn't quick or clean. In the inner solar system, dozens of embryos competed for the available material, colliding with each other in a chaotic dance that lasted tens of millions of years. Each collision was violent, generating enough heat to melt rock, potentially vaporizing volatile substances, reshaping the growing planets. Some collisions were catastrophic, shattering bodies into fragments. Others were mergers, two embryos becoming one, their fates permanently joined. Imagine the inner solar system during this period. Space between the orbit of Mercury and Mars filled with dozens of moon-sized to Mars-sized bodies, each one a potential planet. Their orbits crossed and recrossed. Close encounters happened regularly, each one altering velocities and orbital elements. The gravitational dance was intricate and unpredictable. Computer simulations show that the outcome of this process is highly stochastic, meaning that random factors play a large role. Which embryos collide with which? When those collisions occur, whether they result in mergers or disruptions, all these factors introduce an element of chance into planet formation. Some embryos grew by accumulating material more efficiently than others. Perhaps they happened to orbit in a region with more planetesimals. Perhaps their orbits brought them into contact with multiple other embryos in rapid succession. Perhaps they were simply lucky, surviving close encounters that could have disrupted them. These embryos became the seeds of the terrestrial planets, gradually accumulating mass while clearing their feeding zones of smaller bodies. The collisions themselves were events of incredible violence. When two Mars-sized bodies collide at several kilometers per second, the energy released is beyond human experience. The impact vaporizes rock, creates a fireball that can engulf both bodies, and sends debris flying in all directions. Some of this debris falls back onto the merged body, adding to its mass. Some escapes into space, lost forever, and some enters orbit around the merged body, where it might coalesce into moons or gradually spiral inward and accrete. The heat generated by these impacts kept the growing planets molten. A fully molten planet allows differentiation to occur rapidly. Dense materials, primarily iron and nickel, sink toward the center under gravity, forming a metallic core. Lighter materials, silicate minerals, float to the surface, forming the mantle and eventually the crust. This differentiation is crucial for the final structure of terrestrial planets. Without it, Earth would be a homogeneous mixture of rock and metal, without the layered structure of core, mantle, and crust that we observe. Throughout this process, the disk of gas and dust that had given birth to these growing worlds continued to evolve. The gas slowly accreted onto the sun, or was driven away by stellar winds. The dust either stuck together into larger bodies or drifted inward and was lost. The disk was fading, its time running out. The entire gas disk phase, during which giant planets could form by capturing hydrogen and helium, lasted only a few million years. Once the gas dispersed, any planetary cores that hadn't yet captured atmospheres would remain rocky. The window for gas giant formation was narrow, and only the most rapidly growing cores beyond the frost line made it in time. And in this race against dissipation, one planet in particular would form with remarkable speed, altering the fate of everything else in the nascent solar system. That planet was Jupiter. Jupiter's birth and dominion. The story of the solar system's architecture cannot be told without understanding Jupiter. It was the first planet to form, and its influence on everything that came after was profound, reshaping the disk, scattering planetesimals, and very nearly preventing the terrestrial planets from forming at all. Jupiter began as a planetary embryo beyond the frost line, at a distance of perhaps 3.5 astronomical units from the young Sun. This location was crucial. Beyond the frost line, the availability of water ice, along with other volatile ices, meant that there was roughly 3 times as much solid material available compared to the inner solar system. This abundance allowed planetary cores to grow faster and larger. Within just a few million years, perhaps even less than a million years, Jupiter's core reached a critical mass of approximately 10 to 20 Earth masses. This threshold marked a transition. Up to this point, Jupiter had been growing primarily by accumulating solid material, planetesimals and pebbles. But at 10 to 20 Earth masses, something dramatic happened. The core became massive enough to gravitationally capture and retain gas from the surrounding disk. Hydrogen and helium began to fall onto the growing planet, first slowly, then with increasing rapidity. As the envelope of gas around the core grew more massive, it pulled in even more gas, creating a runaway accretion process. Over the next several 100,000 years, Jupiter ballooned to hundreds of Earth masses, eventually accumulating more mass than all the other planets combined. The planet that emerged from this process was fundamentally different from the terrestrial worlds. Jupiter's core, that initial seed of rock and ice, made up only a small fraction of its total mass. The vast majority was gas, primarily hydrogen and helium, compressed by gravity into exotic states. Deep within Jupiter's interior, the pressure is so intense that hydrogen becomes metallic, conducting electricity like a metal, a state of matter that doesn't exist naturally on Earth. But Jupiter didn't simply grow in place. The presence of the gas disk meant that the planet was embedded in a flowing, rotating sea of material. And this gas exerted forces on the planet through gravitational interactions, forces that would change Jupiter's orbit in a process called planetary migration. The physics of migration is subtle but well understood. As Jupiter orbited the Sun, its gravity pulled on the gas in the disk, creating spiral density waves that propagated both inward and outward from the planet. These waves exerted torques on Jupiter. The inner waves, propagating sunward through denser gas, exerted a negative torque, pulling Jupiter inward. The outer waves, propagating outward through less dense gas, exerted a positive torque, pushing Jupiter outward. For a massive planet like Jupiter, the inner torque typically dominated, resulting in a net inward migration. Jupiter began to spiral toward the Sun. This wasn't a gentle drift. Jupiter was massive enough to open a gap in the disk, clearing away most of the gas in its immediate vicinity. This type of migration, called Type 2 migration, is controlled by the viscous evolution of the disk itself. As material in the gap tried to fill back in, it was continuously swept away by Jupiter's gravity. The planet became linked to the disk's evolution, moving inward as the disk material accreted onto the Sun. As Jupiter migrated, it carved a path of destruction through the early solar system. In the region that would become the asteroid belt, planetesimals and embryos found their orbits perturbed by Jupiter's gravity. Some were scattered inward, hurled toward the Sun. Others were flung outward, possibly ejected from the solar system entirely. Still others had their orbital eccentricities increased, putting them on crossing orbits with other bodies, leading to violent collisions. Computer simulations of this early migration suggest that Jupiter reached a distance of approximately 1.5 astronomical units from the Sun, roughly where Mars orbits today. If Jupiter had kept going, had continued its inward migration, it would have ploughed through the region where the terrestrial planets would form, scattering their building blocks into the sun. Earth would never have existed. Venus, Mercury, none of them. The inner solar system would have been swept clean. This scenario isn't hypothetical. We see its outcome in other planetary systems. The first exoplanet discovered around a sun-like star, 51 Pegasi b, is a gas giant with about half of Jupiter's mass orbiting at just 1/20th of an Earth's distance from its star. A year on 51 Pegasi b lasts just over 4 days. These hot Jupiters, as they've come to be called, are thought to be planets that formed farther out and migrated inward through their protoplanetary disks, eventually settling into these scorching orbits. Many of these systems show no evidence of inner rocky planets. If they once had them, they were destroyed during the migration. Our solar system was heading toward the same fate. Jupiter was spiraling inward, the inner disk was being disrupted, and the window of time during which the gas disk would remain was closing. Within another few 100,000 years, Jupiter might have reached the inner solar system, and our story would have ended before it truly began. But something stopped Jupiter. Something reversed its course and pushed it back outward, saving the inner solar system from obliteration. That something was Saturn. Saturn's rescue mission. If Jupiter is the protagonist of the solar system's formation story, then Saturn is the hero who arrives at the crucial moment to change the course of events. Without Saturn, without its specific timing and mass, our planetary system would look completely different if terrestrial planets existed at all. Saturn formed after Jupiter, also beyond the frost line but at a greater distance from the Sun. Like Jupiter, it began as a solid core that eventually grew massive enough to capture gas from the disk. But Saturn had a disadvantage. It formed in a region where material was less abundant and where the disk was already being perturbed by Jupiter's gravity. As a result, Saturn's growth was slower and it remained less massive than Jupiter, reaching only about 1/3 of Jupiter's final mass. But Saturn had one crucial advantage. Its smaller mass meant it could migrate inward faster than Jupiter. In the Type II migration regime, the rate of migration depends on the viscous properties of the disk and the mass of the planet. A less massive planet experiences less resistance from the disk and can move more quickly. While Jupiter was slowly spiraling sunward, Saturn was catching up from behind. This chase had a predetermined end. When two massive planets migrate inward, they eventually reach a configuration where their orbital periods are related by simple integer ratios. These are called mean motion resonances, and they occur when the gravitational tugs between the planets reinforce each other at regular intervals. The most important resonance for the early solar system was the 3-to-2 resonance. For every 3 orbits Jupiter completed, Saturn completed exactly 2. When Jupiter and Saturn entered this resonance, everything changed. The resonance locked the two planets together, and their gravitational interactions began clearing the gas from the region between them. A gap formed in the disk, a zone largely empty of gas, separating an inner disk inside Jupiter's orbit from an outer disk beyond Saturn's orbit. With no gas between them to mediate the migration, the balance of torques acting on the planets shifted. Here's where the physics becomes beautifully counterintuitive. Jupiter, being more massive, had opened its own gap in the disk even before Saturn caught up. The negative torque from the inner disk and the positive torque from the outer disk had resulted in a net inward migration. But with Saturn now present and locked in resonance, Saturn effectively cleared the outer disk material that had been exerting a negative torque on Jupiter from beyond. Meanwhile, the inner disk, that ring of gas still orbiting between the Sun and Jupiter, continued to pull on Jupiter. But now this inner tour was pulling on both planets, and because they were locked together by resonance, they moved as a pair. The result was surprising. The two planets began migrating outward. This is called the Grand Tack, named after a sailing maneuver where a boat changes direction. Jupiter and Saturn had tacked, reversing course, now moving away from the Sun instead of toward it. The outward migration continued as long as the gas disk persisted, which was likely a few 100,000 years at most. Eventually, Jupiter settled into an orbit at approximately 5.2 astronomical units from the Sun, close to where it remains today. Saturn initially stopped around 7 to 8 astronomical units, though it would later migrate farther out to its current position at 9.5 astronomical units through other processes that occurred after the gas disk had dispersed. This Grand Tack had profound consequences for the solar system's architecture. As Jupiter migrated inward and then outward, it passed through the region that would become the asteroid belt twice. During its inward journey, it scattered material, flinging some objects toward the Sun and others outward. On its return trip, it stirred the region again, mixing material from the inner and outer solar system. This explains one of the long-standing mysteries of the asteroid belt, why it contains both dry, rocky asteroids thought to have formed in the inner solar system and carbonaceous, water-rich asteroids thought to have originated from the outer regions. But the most important consequence of the Grand Tack was what happened to the inner solar system. Jupiter's migration truncated the disk of material inside its orbit. When Jupiter reached 1.5 astronomical units, it cleared away or scattered most of the solid material beyond about 1 astronomical unit. This left a narrow annulus of material, a ring of planetesimals and embryos confined to the region between the Sun and 1 astronomical unit, roughly the distance at which Earth would form. This truncation explains one of the great mysteries of our solar system: why Mars is so small. Mars has only about 10% of Earth's mass, far smaller than what simulations of terrestrial planet formation typically produce. Before the Grand Tack model, simulations that started with planetesimals distributed throughout the inner solar system usually ended up with a Mars mass planet that was 3 to 10 times more massive than the actual Mars. The problem was that there was too much material in Mars's region. But if Jupiter truncated the disk at 1 astronomical unit, then there simply wasn't much material left for Mars to accrete. Mars likely formed in a zone that had been depleted by Jupiter's migration, a region on the edge of the truncated disk. It grew from whatever scraps remained, never accumulating enough mass to become a true Earth-like planet. Mars, in a sense, is a survivor, a planetary embryo that grew as large as it could from limited resources, then found its growth permanently stunted. The Grand Tack also explains the timing of terrestrial planet formation. After Jupiter and Saturn migrated outward and the gas disk finally dispersed, which occurred roughly 3 to 10 million years after the Sun formed, the terrestrial planets could begin their final assembly. The annulus of material left behind by Jupiter's migration became the feeding zone for Mercury, Venus, Earth, and Mars. These worlds grew over the next 50 to 100 million years through collisions among the planetary embryos trapped in this narrow region. Without Saturn's intervention, without the Grand Tack, our solar system would likely resemble the many hot Jupiter systems we've discovered around other stars. Jupiter would have migrated to the inner system, scattering or consuming the building blocks of the terrestrial planets. Saturn itself might have followed, ending up as a warm Saturn in a close orbit around the Sun. The outer solar system might contain a few icy worlds, but the inner system would be barren or populated by whatever small remnants could survive in Jupiter's shadow. Instead, Saturn caught up to Jupiter at just the right moment, the two entered resonance at just the right location, and the inward migration reversed. The inner disk was preserved, albeit truncated and depleted. The stage was set for terrestrial planets to form. Earth became possible. It's worth pausing to consider the role of chance in all this. If Saturn had formed a bit later, or a bit farther out, it might not have caught up to Jupiter in time. If the disk properties had been slightly different, the resonance might not have produced outward migration. If Saturn had been too small or too large, the balance of forces might not have worked. The Grand Tack required a specific set of circumstances, a particular choreography of mass, timing, and orbital dynamics. How common are these circumstances? We don't know for certain. Among the exoplanetary systems discovered so far, we see many hot Jupiters, suggesting that inward migration without a reversal is common. But we also see systems with cold Jupiters, giant planets, at larger orbital distances, which suggests that some systems experience processes similar to the Grand Tack. The frequency of Saturn-like planets in systems with Jupiter-like planets is an active area of research, and preliminary results suggest that such companion giants are not rare, though neither are they universal. What we can say is this: our solar system's architecture required the Grand Tack or something very much like it, and the Grand Tack required Saturn. In a very real sense, we owe our existence not just to Jupiter, the solar system's giant, but to Saturn, the planet that stopped the giant's destructive march. With Jupiter and Saturn now in the outer system, and the gas disk beginning to fade, the inner solar system could at last settle into the process of building rocky worlds. But even with the giants moved out of the way, the formation of the terrestrial planets would prove to be a violent, chaotic affair, taking 10 times longer than the formation of Jupiter and involving countless collisions, some of which would prove crucial for Earth's eventual habitability. The inner rocky worlds take shape. After the gas disk dispersed, roughly 3 to 10 million years after the Sun's birth, the inner solar system was left with a collection of planetary embryos and smaller planetesimals orbiting within a zone extending from close to the Sun out to about 1 astronomical unit. These embryos, each with masses ranging from about 1% of Earth's mass to perhaps 10%, represented the building blocks from which Mercury, Venus, Earth and Mars would form. But they wouldn't simply grow smoothly into planets. Instead, their formation would require millions of years of gravitational interactions and collisions, a chaotic period that planetary scientists call the late stage of terrestrial planet accretion. Without gas in the disk to dampen their orbits, the embryos' gravitational interactions with each other became the dominant force shaping their evolution. Each close encounter between embryos would slightly perturb their orbits, changing their eccentricities and inclinations. Over time, these perturbations accumulated, causing the orbits to cross. When orbits crossed, collisions became inevitable. Computer simulations of this process, run thousands of times with slightly different initial conditions, reveal common patterns. Typically, dozens of embryos start in the inner solar system. Over tens of millions of years through a series of collisions and mergers, these dozens consolidate into a handful of planets. The process is violent and stochastic, meaning that chance plays a large role in determining which embryos merge with which, and where the final planets end up. These simulations usually produce 3 to 5 terrestrial planets in the inner solar system, often with masses and orbits roughly similar to Mercury, Venus, Earth, and Mars. But the details vary considerably from simulation to simulation. Sometimes Mars ends up larger, sometimes smaller. Sometimes an additional planet forms between Venus and Earth. Sometimes Mercury doesn't form at all. The stochasticity reflects the chaotic nature of the process. Small differences in initial conditions lead to large differences in outcomes. Let's consider each of the terrestrial planets and what we know about their formation. Mercury, the innermost planet, is peculiar in several ways. Despite being the smallest terrestrial planet, it has an unusually large iron core relative to its total mass. The core makes up about 60% of Mercury's mass, compared to about 33% for Earth. This high core-to-mantle ratio has led to the hypothesis that Mercury suffered a giant impact that stripped away much of its rocky mantle, leaving behind a planet dominated by its iron core. An alternative possibility is that the intense heat and solar wind in Mercury's region prevented volatile materials from condensing or caused them to be lost, naturally leading to a more iron-rich planet. The truth may involve some combination of both scenarios. Venus, often called Earth's twin because of its similar size and mass, formed closer to the Sun than Earth, at about 7/10 of an astronomical unit. Despite their similar bulk properties, Venus and Earth diverged dramatically in their surface conditions. Venus's proximity to the Sun meant it received nearly twice the solar energy Earth receives, and this difference appears to have triggered a runaway greenhouse effect early in Venus's history. Any water Venus may have had evaporated into the atmosphere, where ultraviolet light from the Sun broke the water molecules apart. The hydrogen escaped to space, while the oxygen combined with the rocks on the surface. Carbon dioxide accumulated in the atmosphere, creating the hellish, high-pressure hothouse world we see today. Venus's formation likely resembled Earth's, but its location determined its fate. Earth's formation is, naturally, of particular interest to us. Our planet likely grew through a series of giant impacts between embryos, each collision adding mass and generating tremendous heat. The heat from these impacts kept Earth's surface molten for much of its formation, creating a magma ocean that may have been hundreds of kilometers deep. As Earth grew larger and its gravity stronger, impacts became more energetic, releasing enough energy to vaporize rock. The final major impact in Earth's formation occurred roughly 30 to 50 million years after the Sun formed, perhaps as late as 100 million years according to some estimates. This was the Moon-forming impact, when an object about the size of Mars, given the name Theia, struck the proto-Earth in an oblique collision. The impact was catastrophic. Computer simulations suggest that Theia's core merged with Earth's core, while debris from both Theia's mantle and Earth's mantle was flung into orbit around Earth. This debris quickly, within just a few hundred to a few thousand years, coalesced to form the Moon. The Moon-forming impact had several important consequences. It added significant mass to Earth, perhaps 10% of Earth's final mass. It added angular momentum, speeding up Earth's rotation. The young Earth immediately after the impact may have had a day lasting perhaps 5 to 6 hours. The impact may also have delivered volatile materials to Earth's interior, including potentially some of the water that would later fill the oceans, and the formation of the Moon itself would prove crucial for Earth's long-term habitability, stabilizing Earth's axial tilt and creating tides that may have played a role in the development of life. Mars represents the most puzzling of the terrestrial planets. As discussed earlier, its small size is likely explained by the Grand Tack's truncation of the inner disk. But Mars's composition also tells us something important about terrestrial planet formation. Isotopic analyses of Martian meteorites reveal that Mars has a distinct chemical signature compared to Earth and Venus, particularly in isotopes of elements like oxygen, titanium, and chromium. This suggests that Mars formed primarily from material in a different region of the disk than Earth and Venus. One scenario that can explain this is that Mars formed slightly farther out and was never fully incorporated into the annulus of material that built Earth and Venus. It remained in a separate feeding zone, growing from material that had a different isotopic heritage. Mars's small size meant it cooled faster than Earth, and its geological activity ceased earlier. Its low gravity meant it could not retain a thick atmosphere, and without a strong magnetic field to protect it, the solar wind gradually stripped away what atmosphere it had. The once warmer, wetter Mars we see evidence for in the geological record gave way to the cold, dry desert world we observe today. The entire process of building these four worlds took roughly 50 to 100 million years, perhaps as long as 150 million years for the very last major impacts. During this time, the terrestrial region of the solar system was a shooting gallery, with embryos and planetesimals colliding, merging, and being destroyed. The heat generated by these impacts kept the growing planets molten, or partially molten, allowing dense materials like iron to sink toward the center and lighter materials like silicates to float to the surface, a process called differentiation. By the time terrestrial planet formation was complete, roughly 100 million years after the Sun's birth, the inner solar system had settled into a configuration of four rocky worlds, each distinct, each shaped by its particular history of formation and its distance from the Sun. Mercury, small and dense, hugging close to the Sun's heat. Venus, Earth's twin in size but an inferno in conditions. Earth, with its large moon, abundant water, and temperate surface. And Mars, small and distant, a world of lost potential. These four worlds grew from the truncated disk left behind by Jupiter's Grand Tack. Their specific masses, compositions, and orbits reflect the chaotic, collision-dominated process of late-stage accretion. In a sense, Earth is the result of a particular sequence of collisions, a specific series of mergers among embryos whose orbits happen to cross at particular times. Had Jupiter not performed the Grand Tack, had Saturn not caught up at just the right moment, these worlds would never have formed. And had the stochastic process of terrestrial accretion played out slightly differently, Earth itself might be substantially different, perhaps larger or smaller, wetter or drier, with or without a large moon. The terrestrial planets were the last of the major worlds to reach their final masses, but the solar system's evolution was far from over. The giant planets, Jupiter and Saturn, along with Uranus and Neptune, would undergo further migrations hundreds of millions of years later, reshaping the outer solar system and triggering a late bombardment of the inner planets. And the architecture that emerged from all these processes, the specific arrangement of planets we see today, would prove to be rare among the planetary systems we've discovered around other stars. The architecture of stability. Stand back and look at the solar system as a whole, and a pattern emerges. 4 small rocky planets in the inner system, with masses ranging from about 3% of an Earth mass for Mercury to just over 1 Earth mass for Venus. Then a gap, the asteroid belt, where no planet formed. Then 4 giants in the outer system, Jupiter at 318 Earth masses, Saturn at 95 Earth masses, Uranus at 14.5 Earth masses, and Neptune at 17 Earth masses. The masses generally increase as you move outward from the Sun, with one exception. Mercury is smaller than Venus and Earth, and Uranus is slightly less massive than Neptune. But the overall trend is clear. Small rocky worlds near the Sun, giant worlds farther out, with the giants themselves arranged roughly in order of decreasing mass. This configuration, what planetary scientists now call an ordered system, seemed natural, perhaps even inevitable, until we began discovering planets around other stars. The orbits of these planets add another layer to the pattern. All 8 planets orbit in the same direction the Sun rotates. Their orbits are roughly circular, with eccentricities, the measure of how elliptical an orbit is, all below about 0.06. For reference, a perfect circle has an eccentricity of 0, and a very elongated ellipse approaches one. The planet's orbits also lie close to the same plane, with inclinations the tilt of an orbit relative to Earth's orbital plane, mostly less than a few degrees. Mercury is the exception with an inclination of 7 degrees, and Pluto, if we include it, has an extreme inclination of 17 degrees. This coplanarity, the arrangement of orbits in nearly the same plane, is a direct inheritance from the protoplanetary disk. Because the planets formed from material in a flattened disk, they naturally ended up orbiting in the disk's plane. The low eccentricities reflect a more subtle aspect of the formation process. In systems with multiple planets, gravitational interactions tend to excite eccentricities, making orbits more elliptical. But gas in the disk can dampen these eccentricities, circularizing the orbits. The terrestrial planets formed after the gas dissipated, so their low eccentricities suggest that their formation was relatively gentle, without strong gravitational stirring from other massive bodies. The spacing of the planets follows another interesting pattern, though not a perfect one. There's an old observation, dating back to the 18th century, called the Titius-Bode law, which suggested that planetary distances follow a simple mathematical progression. While the law isn't truly fundamental and breaks down for Neptune, it does capture something real. Planets tend to be spaced at regular intervals when measured in logarithmic terms. This spacing is related to orbital resonances and the stability of gravitational interactions between planets. Speaking of stability, the configuration we see today is stable over timescales of billions of years. Computer simulations of the solar system's dynamics, integrated forward in time for billions of orbits, show that the planetary orbits remain relatively stable, not crossing or leading to ejections or collisions. There's some chaos in the system. The orbits are not perfectly predictable over arbitrarily long timescales, but the chaos is mild enough that the architecture persists. This stability wasn't necessarily guaranteed. The outer planets, particularly Uranus and Neptune, likely didn't form in their current locations. Evidence suggests they formed closer to Jupiter and Saturn, perhaps in a more compact configuration. The Nice model, named after the city in France where it was developed, proposes that the giant planets underwent a dynamical instability roughly 500 to 700 million years after the solar system formed. This instability, possibly triggered by gravitational interactions with a massive disk of planetesimals beyond Neptune's orbit, caused the planet's orbits to change dramatically. In the Nice model's scenario, Jupiter migrated slightly inward while Saturn, Uranus, and Neptune migrated outward. Neptune and Uranus were scattered outward by close encounters with Jupiter and Saturn, ending up in the distant orbits they occupy today. This migration and scattering had profound effects on the rest of the solar system. It scattered the planetesimal disk beyond Neptune, creating the Kuiper belt of icy bodies we observe today. It destabilized the asteroid belt, causing a spike in impacts on the inner planets known as the Late Heavy Bombardment. Some of the water on Earth may have been delivered during this bombardment by comets, and water-rich asteroids scattered inward. The exact details of the Nice model are still debated, and alternative scenarios exist. But the general picture, that the giant planets migrated after the gas disk dispersed, seems increasingly likely. This late migration was different from the gas disk-driven migration that produced the Grand Tack. Instead, it was driven by gravitational scattering and interactions with planetesimals, a process that can occur long after the protoplanetary disk has disappeared. The end result of all these processes is the stable, ordered architecture we observe today. But as we've begun to survey planetary systems around other stars, we've discovered that this architecture, which seemed so natural to us, is actually uncommon. What we don't have. In science, sometimes what you don't see is as important as what you do see. The absence of something can reveal as much about physical processes as its presence. And when we look at our solar system, two absences stand out. We have no super-Earths, and we have no hot Jupiters. Let's start with super-Earths. These are planets with masses between Earth's and Neptune's, roughly 2 to 10 times Earth's mass. When the Kepler Space Telescope began surveying thousands of stars for transiting planets, super-Earths emerged as one of the most common types of exoplanets. They appear around a significant fraction of Sun-like stars, often in compact systems with multiple super-Earths orbiting closer to their star than Mercury orbits the Sun. These planets don't exist in our solar system. There's nothing between Earth at 1 Earth mass and Uranus at 14.5 Earth masses. This gap spans more than an order of magnitude in mass, a huge missing range. Why? The leading explanation relates to the formation process and the availability of gas. Planets that grow cores larger than about 2 Earth masses while gas is still present in the disk will begin to accrete thick hydrogen and helium atmospheres, ballooning up into mini Neptunes or gas giants. Planets that don't reach this critical mass before the gas disperses will remain rocky, unable to capture significant atmospheres. This creates a natural divide. Below about 2 Earth masses you get rocky super-Earths. Above it you get mini Neptunes with hydrogen envelopes. There's even observational evidence for this divide. Studies of exoplanets have revealed something called the Fulton Gap, a relative scarcity of planets with radii between about 1.5 and 2 times Earth's radius. This gap seems to separate rocky super-Earths from gaseous mini-Neptunes, and it may represent the critical threshold at which planets transition from rocky to gas-rich. Earth and Venus sit just below this critical threshold. They grew slowly enough that by the time they reached their final masses, the gas disk had dissipated. They couldn't capture hydrogen envelopes, so they remained rocky worlds. But why didn't any planet in our inner solar system grow to 2 or 3 Earth masses, massive enough to become a super-Earth, but not so massive as to become a mini-Neptune? The answer likely relates to the Grand Tack. By truncating the inner disk at 1 astronomical unit, Jupiter limited the amount of solid material available to build planets. The terrestrial planets formed from a relatively narrow annulus of material, and this constraint kept them small. In systems without a Grand Tack or similar truncation event, where solid material extends farther and is more abundant, planets can grow larger, reaching the super-Earth mass range. There's another possibility as well. Perhaps Jupiter's inward migration actually swept away proto-super-Earths that had begun to form. Some models suggest that the first generation of planets in the inner solar system may have been destroyed as Jupiter migrated inward, their building blocks scattered into the Sun. When Jupiter reversed course, the material left behind could only form smaller Earth-sized planets. The absence of hot Jupiters in our solar system is less surprising. Hot Jupiters, giant planets orbiting very close to their stars with orbital periods of just a few days, occur around only about 1% of Sun-like stars. Their rarity suggests they require specific formation conditions. Most scenarios for hot Jupiter formation involve inward migration through the gas disk, similar to what Jupiter experienced during the Grand Tack, but in hot Jupiter systems the migration never reversed. Perhaps these systems lacked a Saturn-like companion to stop the inward drift, or perhaps the disk properties were different in ways that prevented outward migration. The existence of hot Jupiters was one of the great surprises of exoplanet science. Before their discovery, most theorists believed that giant planets could only form beyond the frost line and would remain there. The discovery of 51 Pegasi b in 1995, a Jupiter-mass planet orbiting its star every 4 days, shattered this assumption and forced a reimagining of planet formation theory. Migration, once considered a minor effect, became central to understanding planetary system architectures. Our solar system, with its cold Jupiter at 5 astronomical units, represents the alternative outcome, migration that began but was stopped or reversed. This outcome appears to be more common than hot Jupiters, but still far from universal. Many systems have been found with giant planets at intermediate distances, neither hot Jupiters nor cold Jupiters like ours, suggesting a wide range of migration histories. There's another absence worth noting. We lack planets in the asteroid belt region. Between Mars at 1.5 astronomical units and Jupiter at 5 astronomical units, there's a broad gap containing only asteroids, none larger than about 1,000 kilometers in diameter. This gap is a direct consequence of Jupiter's formation and migration. The Grand Tack scattered material from this region, depleting it so thoroughly that no planet could form. The asteroids that remain are the survivors, leftovers from planet formation that never coalesced into a world. Some exoplanetary systems show similar gaps, regions empty of planets, but filled with debris disks of asteroids and comets. These gaps are often interpreted as evidence for unseen planets that have cleared their orbits. In our case, the gap reflects not the presence of a planet in the gap itself, but the disruptive influence of Jupiter's migration through that region. What we don't have, then, tells a story. No super-Earths because the inner disk was truncated and depleted. No hot Jupiter because Saturn stopped Jupiter's migration. No planet in the asteroid belt because Jupiter scattered that region. Each absence points back to the specific history of our solar system's formation, the particular sequence of events that led to the architecture we observe. And when we place our solar system in the context of the thousands of exoplanetary systems now known, these absences, combined with the specific arrangement of what we do have, paint a picture of a rare configuration. Are we rare? Over the past 3 decades, astronomers have discovered more than 6,000 confirmed exoplanets orbiting nearly 4,000 different stars. This represents a tiny fraction of the Milky Way's hundreds of billions of stars, but it's enough to begin drawing statistical conclusions about how common different types of planetary systems are. One of the first major findings was that planetary systems are common. Most stars, it appears, have at least one planet, and many have multiple planets. This was a profound discovery. It meant that the solar system wasn't a fluke, that planet formation is a natural outcome of star formation. The universe is full of worlds. But as the catalogue of exoplanets grew, another pattern emerged. Most of these planetary systems don't look like ours. The first exoplanets discovered were hot Jupiters and other massive planets in close orbits, an artifact of the detection methods used at the time. But as detection techniques improved and biases were better understood, a more complete picture emerged. And in that picture, our solar system appears unusual. A recent study categorized multi-planet exoplanetary systems into 4 basic types based on how planetary masses vary with distance from the star. Ordered systems, like ours, have masses that generally increase with distance. Anti-ordered systems have masses that decrease with distance. Mixed systems show no clear trend, with masses varying irregularly. Similar systems have planets all of similar mass. Of these 4 categories, similar systems are the most common. The TRAPPIST-1 system, with 7 Earth-sized planets all bunched together in orbits closer than Mercury's, is a perfect example. All 7 planets have masses within a factor of 2 of each other, and they're all rocky worlds of similar size. This peas-in-a-pod architecture appears to be extremely common in the exoplanet population. Ordered systems, by contrast, represent only about 1 to 5% of the multi-planet systems analysed in this study. We are, in this sense, rare, but there are important caveats to this conclusion. First, observational bias remains a significant factor. Our detection methods are most sensitive to large planets close to their stars and least sensitive to small planets at large distances. A system identical to our solar system but around a distant star would be very difficult to detect with current technology. Jupiter, despite its size, would require observing multiple 12-year orbital periods to confirm its presence. Earth would be nearly impossible to detect. This means we're likely undercounting solar system analogues in the exoplanet catalogue. Second, the statistics are based on systems with at least 2 detected planets, but many stars have only 1 detected planet so far. As monitoring continues and more planets are discovered in these systems, the statistics may shift. A system currently classified as having 1 hot Jupiter might eventually reveal a cold Jupiter farther out, changing its classification. Third, recent surveys have begun finding more cold giant planets at larger orbital distances, suggesting that Jupiter-like planets at Jupiter-like distances may be more common than early exoplanet catalogues suggested. One study found that cold Jupiters occur around about 10% of Sun-like stars. This is encouraging for finding solar system analogues, as the presence of a cold Jupiter may be a signpost for an inner system of rocky planets. But even accounting for these caveats, our solar system appears to be on the rare end of planetary system architectures. Several features contribute to this rarity. The combination of inner rocky planets and outer gas giants, widely separated, is less common than compact systems where all the planets orbit close to the star. The lack of super-Earths, the most common type of exoplanet, makes our inner solar system unusual. The relatively low eccentricities of our planetary orbits are somewhat unusual. Many exoplanetary systems show highly elliptical orbits, suggesting more dynamically violent histories. The specific spacing and number of planets, 8 major worlds spanning 2 orders of magnitude in distance from the Sun, is difficult to match in simulations that don't include something like the Grand Tack. There's another way to think about rarity. Among planetary systems, different architectures may arise from different formation pathways. The Grand Tack represents one such pathway, requiring the formation of 2 giant planets with a specific mass ratio, their capture into resonance at a specific location, and the subsequent outward migration. How often do these conditions occur? Simulations and theoretical work suggest that the Grand Tack or similar scenarios may occur in a significant minority of systems that form giant planets. It's not the most common outcome, but neither is it vanishingly rare. Perhaps 10 to 30% of systems with 2 giant planets might experience something similar, though this remains highly uncertain and depends on disk properties we're only beginning to understand. This is speculative, as the exact percentages depend on uncertain disk properties and formation timescales. But it suggests that while ordered systems like ours are uncommon, they're not unique miracles. It's also important to distinguish between 2 different questions. Is our solar system's architecture rare? And are Earth-like planets rare? These are related but distinct questions. Even if our overall architecture is uncommon, Earth-like planets might be common. They might form in systems with super-Earths, in systems around red dwarf stars like TRAPPIST-1, in systems with different arrangements of giant planets. The connection between architecture and habitability is still unclear. Some researchers argue that having a Jupiter is important for Earth's habitability, either by delivering water via comets or by shielding the inner system from impacts. Others point out that many of the impacts Jupiter causes might not have occurred without Jupiter in the first place, and that systems without giant planets might be equally or more hospitable to life. The anthropic principle looms over these discussions. We find ourselves in a solar system with our particular architecture because we couldn't find ourselves anywhere else. If this architecture is necessary for complex life, then naturally we observe it, regardless of how rare it is. But we don't yet know what's truly necessary. We have a sample size of 1, and biology, especially complex biology, has proven itself remarkably adaptable. What we can say with confidence is that our solar system is one outcome among many possible outcomes of planet formation. The physical processes involved, accretion, migration, gravitational interactions, are universal. But the specific sequence of events, the particular mass of Jupiter, the timing of Saturn's formation, the location where their resonance occurred, these details vary from system to system. And in our system, those details produced an ordered architecture with inner rocky planets and outer giants, a configuration we now know to be uncommon among the planetary systems we've discovered so far. As our detection methods improve, and as we monitor more stars over longer timescales, we'll gain a better understanding of how rare solar system analogues truly are. The ongoing TESS mission, the future Plato mission, and next-generation ground-based telescopes will extend our ability to find smaller planets at larger distances around Sun-like stars. In the coming decades, we may discover dozens or hundreds of true solar system twins, or we may find that such systems are indeed rare, representing a narrow slice of the possible outcomes of planet formation. Either way, the question is not just about statistics, it's about understanding the processes that shape planetary systems and recognizing that the particular world we inhabit, the system of planets we call home, is the product of a specific and uncommon history. The question of why. We've traced the story of our solar system's formation from the collapsing molecular cloud to the disk of gas and dust, from microscopic grains to planetary embryos, from Jupiter's near destruction of the inner system to Saturn's crucial intervention, from chaotic collisions to stable orbits. Along the way, we've seen how a series of events, each shaped by physical laws but each with its own element of contingency, led to the configuration we observe today. But knowing how something happened doesn't always answer why. Why did things unfold this particular way here, in this stellar system, rather than some other way? Why did Jupiter form when and where it did? Why did Saturn follow at just the right time? Why did the Grand Tack occur at 1.5 astronomical units, rather than farther in or farther out? These questions push at the boundaries between determinism and chance, between inevitability and accident. In one sense, the answer is simply that these outcomes followed from the initial conditions of the solar nebula. The disk's mass, its angular momentum, its temperature profile, the distribution of solid materials, all these properties determine what could happen. Jupiter formed first because it was beyond the frost line where solid material was abundant. Saturn followed because that's the time scale on which cores grow at that distance. The resonance occurred at 1.5 astronomical units because that's where Jupiter happened to be when Saturn caught up. But in another sense, this merely pushes the question back a step. Why did our particular nebula have the properties it did? The molecular cloud that collapsed to form the Sun was itself the product of galactic processes, enriched by previous generations of stars shaped by turbulence and magnetic fields in the interstellar medium. Its properties were not designed but emerged from the complex dynamics of the galaxy. There's an element of chance, of contingency, woven through the entire narrative. If the cloud had been slightly more or less massive, if it had been rotating faster or slower, if the triggering event that initiated collapse had occurred at a different time, the outcome might have been different. The solar system might have formed with only one giant planet, or 3, or none. The terrestrial planets might be larger or smaller or absent entirely. Mars might be Earth-sized, and Earth might be the small one. Computer simulations bear this out. When you run simulations of terrestrial planet formation starting from slightly different initial conditions, the outcomes vary. Sometimes you get 4 terrestrial planets, sometimes 3, sometimes 5. Sometimes Earth ends up with a large moon, sometimes it doesn't. The chaotic nature of gravitational interactions means that small differences in the initial conditions can lead to large differences in outcomes. Yet there are constraints. Not everything is possible. The laws of physics, the properties of the disk, the timescales of various processes, these all limit the range of possible outcomes. You can't form a hot Jupiter without migration. You can't form a giant planet without solid cores reaching critical mass before the gas disperses. You can't have widely separated terrestrial and giant planets without some mechanism to clear or deplete the region in between. The Grand Tack provided that mechanism in our solar system, and while the specific details, the exact masses and timing may have been contingent, the general process of migration and resonance is not exotic. It follows from well-understood physics. Many systems likely experience something similar, even if the outcomes differ in detail. This brings us to a question that has echoed through this entire exploration. Was any of this necessary for Earth to become habitable, for life to emerge, for you to be here listening to this story? The honest answer is that we don't know. We have theories and speculations, but no definitive evidence. Some researchers argue that Jupiter's migration was crucial for delivering water to Earth's region, either during the migration itself or later during the late heavy bombardment. Others suggest that without Jupiter to scatter comets and asteroids, Earth would have experienced more impacts, perhaps too many for life to gain a foothold. Still others point out that many of the dangerous objects Jupiter scatters toward Earth wouldn't exist without Jupiter's presence in the first place. The Moon's formation, resulting from that giant impact with Theia, may have been crucial for stabilizing Earth's axial tilt and creating tides that influence the development of life. But the Moon formed as a result of late-stage terrestrial planet accretion, which occurred because Jupiter's Grand Tack left a truncated disk of material. Without the Grand Tack, perhaps Earth never forms at all, or perhaps a different Earth forms in a different configuration, with or without a moon, and life finds a way anyway. We're limited by our sample size. We know life arose on Earth, in this solar system, with this particular history. But we don't know if life requires these specific conditions, or if it could arise in systems with very different architectures. Perhaps super-Earth systems are equally conducive to life. Perhaps small rocky planets around red dwarf stars like the TRAPPIST-1 worlds are habitable despite their different configurations. We simply don't have enough information yet. The anthropic principle offers a kind of answer, though not a satisfying one. If certain specific conditions were required for our existence, then we would necessarily find ourselves in a system with those conditions regardless of how common or rare such systems are. We observe what we can observe because we couldn't exist to observe anything else. But this doesn't tell us whether those conditions were truly necessary or merely sufficient. It doesn't tell us how many other pathways might also lead to life. It doesn't tell us whether our rarity is meaningful or coincidental. What we can say is this: the solar system's architecture, uncommon though it may be, arose from the same physical processes that shape all planetary systems. We're not separate from the patterns we observe in exoplanetary systems, but part of the distribution, residing in a less populated region of the possibility space. Our formation followed natural laws, required no miracles, violated no physics. It simply followed a particular path, one pathway among many, leading to the configuration of worlds we see today. And perhaps that's enough. Perhaps the question of why doesn't require an answer beyond the sequence of hows we've explored. The universe doesn't arrange things according to purpose or design, but according to physical law and probabilistic outcomes. Some configurations are common, others rare. We happen to find ourselves in one of the rarer ones. The vast cosmos continues to form stars and planets, and each system writes its own story, following the same fundamental rules but producing an incredible diversity of outcomes. Some produce hot Jupiters, some produce super-Earth systems, some, perhaps a few percent, produce arrangements like ours, with rocky inner worlds and giant outer planets, separated by a depleted zone, orbiting in rough order of increasing mass, and in at least one such system, on one of those rocky inner worlds, in a thin film of air and water clinging to the surface, life emerged. Complexity arose from simplicity, consciousness from matter, wonder from atoms. Whether this requires a rare arrangement of planets or whether it happens in common configurations as well, we don't yet know, but we know it happened here. Ordinary extraordinariness. So we return to where we began, standing under a night sky, looking up at the planets. Venus bright in the evening, Mars with its reddish glow, Jupiter steady and brilliant, Saturn fainter but present. These aren't just points of light anymore, they're worlds with histories, participants in a vast cosmic story that unfolded over millions of years, a story we're only now beginning to piece together. The solar system felt natural to us because it was all we knew. 4 small rocky planets close to the Sun, 4 giants farther out. It seemed like the obvious way to arrange a planetary system, perhaps the only way, but the universe, as it so often does, surprised us. When we looked at other stars, when we discovered their planets, we found a cosmos of remarkable diversity. Systems nothing like ours, planets in configurations we never imagined, architectures we didn't predict. And in that diversity, our own system stands out. Not as unique, not as impossible, but as uncommon. The ordered arrangement, masses generally increasing with distance, appears in only a small fraction of the multi-planet systems we've discovered. The specific combination of inner rocky worlds and distant giants, the absence of super-Earths, the relatively circular orbits, all these features together paint a picture of a rare configuration. But rarity doesn't mean inexplicable. Every step of our formation followed from the one before it, shaped by gravity and chemistry, by accretion and collision, by migration and resonance. The story we've traced tonight is one of physical processes playing out over millions of years. A cloud collapses, a disk forms, dust sticks together, planets grow, Jupiter migrates inward, Saturn catches up, resonance reverses the migration. The inner disk is preserved but truncated. Terrestrial planets form from what remains. Chaos gradually organizes itself into stability. The Grand Tack, that crucial reversal of Jupiter's migration driven by its resonance with Saturn, stands as perhaps the pivotal event in our solar system's history. Without it, Jupiter would likely have continued spiraling toward the Sun, scattering or consuming the building blocks of the terrestrial planets. Earth would never have formed. We wouldn't be here to contemplate any of this. Saturn, then, deserves recognition as a kind of saviour, though one acting without intent or awareness. Its formation at the right time, at the right distance, with the right mass, allowed it to catch Jupiter and reverse the giant's destructive course. How often this happens in other stellar systems we don't know for certain. But if the frequency of ordered systems in the exoplanet catalogue is any guide, it's not the most common outcome. Perhaps 1 in 10 systems with giant planets experiences something similar. Perhaps fewer. Mars, small and distant, serves as a permanent reminder of the Grand Tack's consequences. Stranded in a depleted region, it could never grow beyond 1/10 of Earth's mass. It's a survivor, a planetary embryo that escaped destruction but never reached maturity. When we look at Mars, we're seeing an artifact of Jupiter's migration, evidence etched in planetary mass for the violence that shaped the early solar system. Earth, by contrast, represents the opposite outcome. It formed in a region where enough material remained after the Grand Tack to build a substantial world. It grew through collisions, each one adding mass and heat. The final giant impact with Theia gave Earth its moon, that large companion that stabilizes our axial tilt and creates the tides. Water accumulated on the surface delivered by asteroids and comets, perhaps augmented by material locked in the planetesimals that built Earth itself. The conditions that allowed life to emerge on Earth were shaped by this history. The planet's size determined by the amount of material available in the truncated inner disk, its composition reflecting the mix of materials that accreted, its distance from the Sun, placing it in the temperate zone, its moon, the product of that final giant impact, its water delivered by the same processes that formed the planet. Would a different configuration have worked? Could life have arisen on a super-Earth, a planet twice Earth's size and 10 times its mass? Could it emerge on one of the TRAPPIST-1 worlds, those 7 Earth-sized planets huddled close to a red dwarf star? We don't know. The question is one of the great scientific inquiries of our time, driving missions to Mars, to Europa and Enceladus, driving the search for biosignatures in the atmospheres of exoplanets. What we know is that it happened here, in this configuration, following this history. The solar system's rarity, if that's what it is, doesn't make Earth special in some cosmic sense. The universe doesn't assign value to different planetary configurations. Rarity and commonality are just statistics, descriptions of how often different outcomes occur. But for us, the inhabitants of this particular rare configuration, it matters. This is the only system we have. These are the only planets we can currently reach. This is home. And perhaps there's something profound in understanding that our home, this collection of 8 worlds orbiting an ordinary star, arose from a sequence of events that produced an uncommon result. It reminds us that the cosmos is vast enough to produce tremendous variety, that the same fundamental processes can lead to wildly different outcomes, that the accident of our particular history is just one story among billions playing out across the galaxy. Somewhere out there, other planetary systems are forming right now. Around young stars, disks of gas and dust are coalescing into worlds. Giant planets are opening gaps, possibly migrating inward or being caught in resonances. Rocky planets are building themselves through collisions. Some of these systems will end up looking like ours. Most won't. Each will tell its own story, follow its own path through the space of possible configurations. And on some of those worlds, perhaps, other beings might someday look up at their own night sky, see their own planets, and wonder about the story of their formation. They might discover, as we have, that their particular arrangement is uncommon, or they might find themselves in one of the more typical configurations and wonder about the rare systems out there, the unusual ones, the ordered ones. Let that thought settle over you. You're resting on a planet that formed through a rare sequence of events, from a disk truncated by a giant planet's migration, assembled through chaotic collisions, orbiting a star that is itself unremarkable among the hundreds of billions in the galaxy. You're part of this rare arrangement, this cosmic accident, this particular throw of gravity's dice. Tomorrow the sun will rise over the same horizon it has risen over for billions of years. Venus will shine in the evening or morning sky. Jupiter will drift slowly through the zodiac. Saturn will continue its 30-year orbit. Rings tilted at their majestic angle. Mars will glow its rusty red. Mercury will dart back and forth near the Sun. Uranus and Neptune will orbit invisibly in the outer darkness. The 8 worlds will continue their ancient dance, the same dance they've performed since the solar system settled into its current configuration, billions of years before the first life stirred in Earth's oceans. And you'll be here, on this rare Earth, in this uncommon system, under this familiar sky. The question of why it all happened this way, why this particular arrangement emerged from the swirling chaos of the protoplanetary disk, that question will remain. Perhaps we'll never have a complete answer. Perhaps the best we can do is understand the hows, the physical processes and probabilistic outcomes, and accept that our existence in this particular configuration is part of the vast experiment the universe is running, testing every possibility, creating every outcome that physics allows. For now, though, as you drift towards sleep, let the wonder of it all wash over you. The rare cosmic arrangement that is your home, the billion-year story compressed into this one evening. The vast universe full of planetary systems, each one different, each one writing its own story in gravity and stone and gas. If you found this journey through time and space meaningful, if these questions about our cosmic origins resonate with you, consider subscribing to this channel or leaving a like. It helps others find their way to these explorations, to these long, quiet conversations about the universe and our place in it. Your engagement, your curiosity, sustains this work. But for now, just rest. The solar system isn't going anywhere. The questions will still be here tomorrow. The 8 planets will continue their orbits, following the paths laid down 4.5 billion years ago. Paths carved by chaos that somehow led to order, violence that somehow produced stability, accidents that somehow resulted in you. Sleep well, knowing you're part of something rare and remarkable. This cosmic arrangement, this uncommon configuration of worlds, this place we call home. Good night.